Hello, this is Miraj Patel, and today we're going to be talking about two parts of the atomic theory unit. And so we're going to be first talking about average atomic mass, and the second part we're going to be talking about what are moles. And so average atomic mass is calculated by finding the relative abundance of elements and multiplying these abundances by their naturally occurring ratio or percentage. And so we'll talk about it a little bit more detailed. And so we pretty much take a weighted average. Like in my school, we have to average the test grades, and the tests weigh 60% while the worksheets weigh 40%. So we first take the separate averages. So let's just say I got 100 on test, and we multiply that by 60%, and we add it, the worksheets. Let's just say I got 95 on a worksheet, so we would multiply 95 times 40% because that's how much it weighs for the overall grade. So pretty much the weighted average part is the part where we multiply by the percentage of the overall. So we pretty much take an average, a weighted average atomic mass is calculated by both the mass and the relative abundance, or the percentage, of the isotopes. And so I know this sounds a little confusing, but on the next slide we'll have the formula. And so if we have these two percentages, so copper 63 is 72.7 abundant, but copper 65 is 27.3 abundant. And so to which will the average mass be closer? Well, if you think about it, 63 is more abundant. It's 72%, while 65 is about 27%. So because there is more 63, it will be closer to this value. So if you think about it, if you have 100 on a test, but then you get or if you get 200s on a test and then you get 170, the grade is going to be closer to 100 because there's two of them. Same thing in this one. Because there's more 63s, copper 63s, it will be closer to 63 than 65. And so here is the formula. So average mass, which is what we need to calculate, is mass 1 times its percent abundance plus mass 2 times percent abundance. And so copper 63 has a mass of 62.93 AMUs and natural abundance of 69.5, while copper 65 has a mass of 64.93 AMU and it has a natural abundance of 30.5. So we plug this in to the equation, so we get copper 63, which is 62.93 times its percentage right here, and we just move the decimal to make it a decimal. And so then we multiply this copper 65 times its abundance, and we add these numbers up, and we get 63.55, and this is just how you calculate it for everything. And so which isotope is in greater relative abundance in natural samples of neon? And if we look at the periodic table, neon has a relative mass of 20.18, so the average is obviously closer to 20. And like we talked about before, if there's more 20, the average will be closer to 20, but if there's more 22, then the average mass will be closer to 22. And so because the average atomic mass is 20.18, we know that there's more 20s because this number is so much closer to 20 than 22. And so think of the grade scenario. If you have 300s but one's like 80, the grade is going to be closer to the hundreds because there's more of them. And same thing with this scenario. And so here's a quick quiz to see what you learned. And so sulfur contains sulfur contained 90% sulfur 32 and 10% sulfur 34. The average atomic mass would be 32.2, 32.9, 33.5, and 34.2. And so you would need a calculator to do this. And so we go back to the formula, and you have to multiply the percentage times the mass, the corresponding mass, plus the mass 2 times its percentage. And so if sulfur contained 90% 32, so 32 times 0.9 plus 34 times 0.1, and if you do that in the calculator, you'll get A. And so pretty much you just have to multiply the percentage times the corresponding mass and add them up. And that's the end of this PowerPoint. And so the next PowerPoint we'll be talking about what is a mole. And so you know, in life we use, measuring amounts, like we use volume to measure things. We use numbers of an object, or we use mass. And back to chemistry, so atoms are so small that we can't really count every single atom because they're so small. We work with billions of atoms at a time. So we can't count them, but we can count it by weighing it. And so that's pretty much what a mole does. And here's an analogy. So a pair of atoms is 2 atoms. A dozen would be 12. A mole is 602.00000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000Just shorten mole to 6.02 and so just shorten mole to 6.02 times 10 to the 23rd. So this is in scientific notation. So when we expand it, we will have, this is the big number, and this is how many particles are in 1 mole. And so a mole is a unit. It's not a spy, it's not a machine for digging tunnels, it's not a burrowing animal or a spot of skin pigmentation. It's just a unit of measurement containing this many particles. And so, by the way, this is called Avogadro's number, or just a mole. And here's this analogy, or a scenario. Could Bill Gates ever become a millionaire? Well, he only has 7 billion right now, and to become a millionaire, he would have to earn 33,000 trillion a day for the next 50 years. So it's not likely, but a mole is a lot, so it's no surprise. And how much water is in the Pacific Ocean? Well, approximately 6.10 to the 20th is equivalent to about 1 mole of particles. So there's almost a mole of milliliters in the ocean, in the Pacific Ocean. So that's just a rough estimate of how much a mole is. And pretty much, here's another analogy. Which weighs more, the elephants or the rabbits? And so obviously, if you know just from experience, that elephants weigh a lot more than a bunch of rabbits. But even though they weigh more, there's still 12 rabbits and 12 elephants. So the mole is like the same thing. A mole of one substance and a mole of another substance have the same number of atoms, but they weigh different. So like a mole of neon weighs 20 grams, while a mole of carbon weighs 12. So it's the same thing. A dozen elephants or a dozen rabbits, they weigh different, but they're the same number. So that's very important. And so, as we already talked about, they're the same number of atoms but weigh differently. And why do we use moles? Well, often, if you want now, if we want to know how many molecules, we can just use a mole. So instead of, it's physically impossible to count every atom. So we just use mole to simplify it. And pretty much the same thing. Um, it's the same thing. We can't really count it all. And even if we had a way to see them, it's just too many atoms or molecules to see all the, count them all. And moles just make it so much easier to count. So pretty much moles really shorten the way we count atoms. So like, if we just know 1 mole of carbon weighs 12 grams and we just know how many grams of carbon we have, we can just quickly figure out the number of moles. And so it's just pretty much like grouping up numbers. So like if you had 36 donuts, why don't we just count them in dozens instead of counting them in every single donut? So like if you had 108 donuts, you can just say there's 9 dozens instead of saying 108 donuts. Same thing. If we had a billion atoms, instead of counting every single one, we can just say it's a decimal of a mole. So that's how moles really help with counting. And so a mole of any substance contains 6.02 times 10 to the 23rd particles. And there's few types of problems. So the first type of problems is just going from moles to particles. And so when you're doing these conversion problems, it's important to set up these fractions, right? So if you have 3 moles of a substance, how many atoms do you have? So when you do these fractions, it's important to have the numerator of the previous fraction to be the same as the denominator of the next fraction. So we have moles, 3 moles here, and 1 mole here, so this is fine. So we multiply it, and then on the top is what we really want the next unit to be. So 3 times 6.02 times 10 to the 23rd gives you the number of atoms. And because these moles cancel, you just get 3 times 6.02 times 10 to the 23rd atoms, and you stay in atoms, and that's what we want. So this is set up correctly. The moles cancel, and type 2 is particles to moles, which is the exact opposite. So you start with particles. So if you start with particles or molecules, you want molecules on the bottom of the next fraction, so these two cancel out like that. And then you put moles on the top with just 1 mole, and that's how you get the number of moles. And so we end with moles, and that's what we want, so that's good. And so here's some scenarios. So type 1, how many molecules are in 2.12 moles of propane gas, C3H8? And so we start with moles and we want molecules. So moles goes on the top. So in the next fraction, 1 mole will go on the bottom, and on the top you put Avogadro's number, 6.02 times 10 to the 3rd atoms. And so moles cancel out, and we have atoms, and we want atoms, so that checks out. And you punch this into your calculator. And it's always important to put parentheses around this whole expression, because we have to do 6.02 times 10 to the 23rd before we multiply with this. So always put parentheses around these scientific notation little abbreviations. And so we get 1.28 times 10 to the 24th atoms in 2.12 moles. And type 2 problem we have next. So we're going from particles to moles. And so we have magnesium is a light metal used in manufacture aircraft, automobile wheels, and tools, and garden furniture. How many moles of magnesium is 1.25 times 10 to the 23rd atoms? So we have atoms and we want to go to moles. So we first list it, and then on the fraction, the next fraction, we need atoms on the bottom, so we put Avogadro's number, 6.02 times 10 to the 23rd atoms. So atoms cancel out. And then on the top, we put the number of moles, so 1 mole And so 1.25 times 10 to the 23rd times 1 mole equals the number of moles. And we get 0.208 moles. And type 2 problem, last one. How many moles is 2.17 times 10 to the 24th molecules of Br? And so we first have molecules and we want to get to moles. So we put molecules on the denominator of the next fraction. So molecules cancel out. So, and then we put 1 mole on the top because that's what we want in the next unit. And we want moles, so this checks out, and so we multiply 2.17 times 10 to the 24th in parentheses divided by parentheses 6.02 times 10 to the 23rd parentheses. So you divide this by this, and we get 3.60, my bad. And the last type of problem, how many atoms are in 1.14 moles? So we want to go moles to atoms, so this is a type 1 problem. And so we have moles, and we want to then we want to get to molecules, so we divide by moles to cancel those out. So 1.14 moles cancels, and then 6.02 times 10 to the 23rd is 1 mole, so 1.14 times this in parentheses gives you this gives you a number of molecules, but it's asking how many atoms are in there. So if we have number of molecules, we know that each molecule has 4. So again, we put the unit we have in the numerator of the first fraction on the denominator of the next. So 1 molecule equals 4 atoms. And so to do these multiple fraction problems, I would just multiply all the top numbers and divide by the bottoms. So 1.14 times 6.02 times 10 to the 23rd in parentheses, I remind you, and 4 atoms, divided by 1. But anything divided by 1 is the same thing, so you can just do the top, and you get 2.75 times 10 to the 24th atoms. And that brings us to the end of our lesson today. And I hope this helped you learn about moles and how to convert from moles to particles. And the next video, we're going to be wrapping up Unit 2, and we're going to be talking about more molar conversions to grams this time. And if you have any questions, ask your teacher, like always. And I hope you have a good day, and we'll see you next time.